thanks for joining me today, bringing your tea. I see that you're also going through a tea phase. I respect that. I wanted to ask you about neural networks. I keep hearing it within Industry 4.0 world. Personally, I'm very interested in what it means. So can you explain a little bit to us, laymen and people and other people in manufacturing industry that might not understand it?
Okay, so yeah, thanks for having me. First thing I would say, neural networks are like or work generally like any other machine learning algorithm. It's just about it, the way it works. It tries to mimic how the brain works and how the neurons are connected and they transfer energy from one to another. And yeah, in fact, what it does is it has an architecture, so it works in different layers that have different number of networks, and basically the information flows from the input side to the output side, and this network, it assigns different weights to the information that comes from the previous layers, the previous neurons. And like that, it models, these weights is what models the network and makes it adapted to the data we have. This way it's able to learn very complex patterns involving many variables. So this is maybe what makes them different than conventional ML techniques.
Okay, so could you expand on that? Why are therefore neural networks better than conventional machine learning techniques?
That's a good point. And the first thing is that they are not better. They have a different purpose.
Okay.
Let's say, depending on the amount of data you have, depending on the amount of variables you have, depending on how clear are the patterns in your data, it's recommended to use one technique or another technique. If you know what's happening, if you know that when some variable is higher than 200 and some variable is lower than 100, then you don't need any ML AI, you have it right there.
Okay.
If you just want to know when two variables that are correlated, this correlation is broken, you don't need ML to that because it would only bring uncertainty. You just compute the correlation and check when this is lost. It's when you have much more complex problems than that you cannot just directly code it in a hard way, if you want, that there is room for these models that are able to capture complex pattern that we cannot see with just with our brain and our knowledge, because maybe we cannot consider 20 variables at the same time and we cannot understand what happens if that variable number 1 changes a bit and the variable 17 changes as well, then what would happen? So we cannot maybe understand all of this in our brain, and then it's where it comes when we can leverage these techniques. And let's say from going to less to more complex, we would have this, the less complex would be these rules. Then there would be some computations like correlations and so on. Then would come the simpler machine learning models like linear regressions, polynomial, you can complicate it, support vector machines, random forests, etc. And at the very end, it would be the neural networks, deep learning. And let's say the more you move from simpler to complex, it's also you move from more to less certainty. So the more you complicate it, the more risk there is that your model might not be reliable. You can put it in this way.
Okay, I didn't mean to ask that, but now that you've mentioned it, a lot of questions are popping in my head. Why would anyone therefore go or decide on going for a less predictable or less certain technique?
Yeah, it's when you have nothing else to work. When you have lots and lots of variables, when we're talking about dozens, hundreds, thousands of variables, hundreds of thousands, even millions of cases. Okay. That is when training a support vector machine, maybe you won't see it finish, like maybe your grandchildren will see it, but then it's when you have to opt for these other techniques. They are techniques that they don't require as much as pre-processing. So let's say that the neural networks are more ready that when you have too much and don't know how to take it from, the neural network can do all the job for you.
Okay.
But ideally, if you can transform the data, extract variables that expose what you are looking for, expose the patterns, and you can then, once you have high value data, it will be better to have any model would capture when the data is good. So then you, in that case, maybe it's not needed to train something as big, as complex as a neural network.
Okay. So correct me if I'm wrong, but from what I'm understanding, we're using neural networks in cases we have a lot of data and variables that we cannot make sense of or cannot humanly process by ourselves. And we're hoping to find some insights that we are completely unaware of.
Absolutely right. And we expect the network to learn it from us and give a response, an educated response for us.
Okay, excellent. Can you give us an example of how this kind of technology would be useful in industry and where in particular it finds its niche?
Sure. I can talk you about a particular case of neural network which are called autoencoders. It has nothing special in terms of neurons and the mathematics inside. It just the architecture is different. It has like a bottleneck in the middle. Like it shrinks. The number of the size of the layers are smaller in the middle, and then it increases the number of items in each layer to match the number of inputs to the number of outputs.
Okay.
And they have many applications like noise reduction for coloring pictures in grayscale. And one of the things that can be used is for also dimensionality reduction. That's an important one. But what we can use it here is for detect anomalies or detect malfunctions. Because what this network does is it tries to, as it reduce dimensions, so it tries to condensate all the information in a very small amount of variables, and then it tries to reconstruct it again. So when you have a case that is very common in the data, it will be very easy from the network to reconstruct it well. When you have a very strange case, a very anomalous case, the network won't have learned that from the training data, and it won't be able to reconstruct this case well. Then you can compare how the network has reconstructed that to what is the real case, and can then explore the mismatches.
And that's where we get anomalies.
That's where we get anomalies. But then there's even a bit more to that, because it can be anomalies of many kinds. But then you can check exactly how each case or from which perspective is difficult to reconstruct, from which variable it's difficult to reconstruct. And then you can see that when it is a certain temperature or vibration that it hasn't been reconstructed well because it's higher than it should be, you can link that to a certain failure pattern. And then you have another case that is the pressure is too low, but the vibrations are stable, then you can link that to maybe some pressure leakage. So you can, each different type of reconstruction error, you can link it to a failure, a business failure pattern.
Okay, that's the discovery part. Once the neural network comes out with what it's seeing as anomalies, we try to associate that with the physical world, and in doing so, actually teach as well.
Indeed, that's the good part. That would translate the mathematics and the numbers to business, to something usable in the real world.
Great, excellent. Thank you, Albert. That was very enlightening. I hope you learned something as well. And if you have any questions, feel free to reach out to us. See you next time.
Thanks again.
No problem.